The first law of thermodynamics tells us energy is conserved, but is that the whole story? What if I told you it doesn't explain why your coffee cools down or why engines can't be 100% efficient? Today, we uncover the blind spots of the first law and dive into the second law that completes the picture. Objectives of the study. By the end of this video, you will identify the limitations of the first law of thermodynamics in describing real-world processes. Understand why energy conservation alone can't explain process direction and efficiency. Get introduced to the second law of thermodynamics and its key concepts like entropy and irreversibility. Learn how the second law explains why some processes happen spontaneously and others don't. Appreciate the importance of these laws in engineering and natural phenomena. Who is this for? Students studying physics, mechanical engineering, or energy systems. Science enthusiasts curious about the laws that govern energy and efficiency. Educators and content creators seeking clear, concise explanations of thermodynamics. Anyone interested in the fundamental principles behind engines, refrigerators, and the natural world. Why the first law of thermodynamics isn't enough. Second law explained. Hey everyone, welcome back to my channel. Today we're talking about a big question in thermodynamics. Why isn't the first law enough to describe how the real world works? We'll break down the limitations of the first law and see how the second law steps in to fill the gaps. Let's get started. First, a quick refresher. The first law of thermodynamics is basically the law of energy conservation. It says, energy cannot be created or destroyed, only transformed from one form to another. Mathematically, it looks like this. Change in U is equal to Q subtract W, where change in U is the change in internal energy, Q is the heat added to the system, and W is the work done by the system. Simple, right? If you add heat to a system, it either increases the system's internal energy or it does work, like moving a piston. Today, we're breaking down a super important equation in thermodynamics. Change in U is equal to Q subtract W. This is the first law of thermodynamics, and it explains how energy moves in any physical system. Let's break it down, simply and visually. This equation tells us the change in a system's internal energy is equal to the heat added to the system, minus the work the system does on its surroundings. Let's look at each part. Change in U, change in internal energy. This is how much energy the system gains or loses internally, like the motion and vibration of molecules inside a gas. If change in U is positive, the system's energy increases. If it's negative, the system loses energy. Q. Heat added. This is the energy transferred into the system due to temperature difference. If you add heat, Q is positive. If the system loses heat, Q is negative. Example, heating up a gas adds energy. W. Work done by the system. This is the energy the system uses to do something physical, like expanding and pushing a piston. If the system does work, W is positive, energy leaves. If work is done on the system, W is negative, energy enters. Let us consider a real-world example, gas in a cylinder. Imagine a piston filled with gas. You heat the gas. Q equals plus 100 joules. The gas expands and does W equals 40 joules of work pushing the piston. Apply the equation. Change in U equals 100 subtract 40 equals 60 joules. So the gas keeps 60 joules of energy internally. That's stored as faster moving molecules, higher temperature. What are our key takeaway? Heat in, work out, the rest stays in the system. This equation helps us track energy in engines, refrigerators, batteries, and even biological systems. So what's the problem? The first law is great at tracking energy, but it doesn't answer some crucial questions like, number one, which way does a process go? Let's say you put an ice cube in hot coffee. The first law says energy moves, sure, but it doesn't say how. Can the ice cube heat up the coffee? Can the coffee freeze that ice cube? In theory, the math works either way, but we know heat flows from hot to cold, not the other way around. The first law doesn't explain that. Number two, what about efficiency? Why can't we build an engine that turns all heat into work? According to the first law, you can keep converting energy forever, but real engines always waste some heat. Number 3. Quality of energy. It treats all forms of energy as equal in quality. But in reality, mechanical work is more useful than low-grade thermal energy. For example, 1 megajoule of work can fully lift a weight, but 1 megajoule of heat at room temperature can't do the same unless it's converted efficiently. Number 4. What is irreversibility? You spill a cup of tea, it spreads out, cools down. Can it ever go back? The first law says nothing about irreversibility. But in real life, most processes can't be reversed without extra energy. Many real-world processes are irreversible, for example, friction, spontaneous mixing. The first law doesn't distinguish between reversible and irreversible processes. Next, we dive into reversible processes, a key concept in thermodynamics that helps us understand the ideal way energy can be transferred. If you want to know what makes a process reversible, why it's important, and how it compares to real-world processes, this video is for you. Let's jump right in. A reversible process is one that can be reversed without leaving any trace, meaning the system and surroundings go back exactly to their original states. Sounds perfect, right? But for that to happen, the process must meet some strict conditions. Conditions for reversibility. For a process to be truly reversible, these 6 conditions must be fulfilled. 1. No friction at all. Friction always generates heat and loss, which makes reversal impossible. 2. No heat transfer with a finite temperature difference. Heat must flow infinitely slowly between bodies of almost identical temperature. What does this mean? When heat moves from one object to another, it usually flows because of a temperature difference. Heat naturally goes from a hotter body to a cooler one. If the temperature difference is large, heat transfer happens quickly but irreversibly, meaning the process can't be undone without extra work. To have a reversible heat transfer, an ideal process, the temperature difference must be infinitesimally small, almost zero. Why infinitely slowly? If the temperatures are nearly the same, heat moves very slowly, allowing the system to stay almost in thermal equilibrium at every step. This slow, gradual transfer means the system is always close to equilibrium, no sudden jumps or losses. The process can, in theory, be reversed by an equally small temperature difference going the other way. There's no generation of entropy, so the process is ideal and reversible. 3. Energy transfer during the forward and reverse process must be exactly the same, both heat and work in and out. This means that for a process to be reversible, when you run it forward and then run it backward, the amount of energy exchanged as heat and work must be identical but in opposite directions. Why is this important? In the forward process, the system might absorb heat Q and do work Q on the surroundings. In the reverse process, the system must give back the same amount of heat Q to the surroundings and have the same amount of work Q done on it. If this condition isn't met, some energy is lost, usually as friction or heat dissipation, and the process becomes irreversible. 4. No free or unrestricted expansion. The system's volume changes must be controlled. When a gas or fluid expands, the way it expands affects whether the process can be reversible or not. Free or unrestricted expansion means the gas expands suddenly and freely into a larger volume without pushing against anything, like a gas suddenly released into a vacuum. In this case, no work is done on the surroundings because the gas isn't pushing against anything. This kind of expansion is irreversible because it happens spontaneously and can't be undone without extra energy input. Why must volume changes be controlled? For a process to be reversible, the expansion or compression must happen slowly and carefully, with the system doing work against an external pressure that is nearly equal to the system's internal pressure. This controlled expansion means the system is always very close to equilibrium. The system can then be compressed back to its original state by reversing the external pressure changes, making the process reversible. 5. No mixing of fluids. Mixing increases entropy and can't be undone spontaneously. When 2 different fluids mix, like oil and water or hot and cold water, They spread out and combine naturally. This mixing is a spontaneous process that increases the disorder, or entropy, of the system. Because entropy increases, the process is irreversible. You can't just separate the fluids again without putting in extra work or energy. Why does mixing increase entropy? Before mixing, the fluids are separate and ordered. After mixing, the molecules are spread randomly and uniformly, increasing disorder. The system moves to a more probable, higher entropy state. Why can't mixing be undone spontaneously? Undoing the mixing would mean decreasing entropy, which doesn't happen naturally. You need external energy or work, like filtering, centrifuging, or distillation, to separate the mixed fluids again. 6. The process proceeds through a series of equilibrium states, meaning the system is always very close to balance. Examples of reversible processes. Some classic examples. Frictionless adiabatic expansion or compression. No heat exchange, no friction. Frictionless isothermal expansion or compression. Constant temperature, no friction. Condensation and boiling of liquids done very slowly at equilibrium. Examples of irreversible processes. In real life, most processes are irreversible. For example, combustion. Energy lost as heat and exhaust gases. Mixing of two fluids. Entropy increases, can't be reversed spontaneously. Processes involving friction always waste energy as heat. Electric current flowing through resistance causes irreversible heat generation. Heat flow from hot to cold, natural and irreversible direction. Why reversible processes matter? You might wonder, why do we even care about reversible processes if they're ideal and impossible to fully achieve? Here's why. Devices like engines and turbines produce more work when the working fluid undergoes reversible processes compared to irreversible ones. Fans, compressors, refrigerators, and pumps require less power input if their processes are closer to reversible. Reversible processes define the maximum efficiency limit. They are the gold standard engineers aim for. Only reversible processes can be accurately represented on thermodynamic property diagrams. The truth is, reversible processes are hypothetical. We can approach but never perfectly achieve them. So, the engineer's challenge is to design systems that operate as close to reversible as possible, minimizing losses and maximizing efficiency. To sum up, reversible processes are ideal, frictionless, infinitely slow, and perfectly balanced energy exchanges. Real processes are irreversible, but understanding reversibility helps us improve designs and push efficiency to the max.